is why are some functions not integrable, and how can one determine whether the given function is integrable or not?
Okay, that's a very good question. So let's take the function sine. Oh, wait a darn second. Oh, wait. So let's take the function cosine x over x as a little bit of an example. So sine x over x, its younger brother, is very well behaved. It is equal to 1 right at its peak over here, then it slowly decreases over time. And of course, it has a defined integral. But then, what about cosine x over x? Well, okay, as it approaches 0, this approaches 1, and this approaches, well, 0, meaning this is going to approach infinity. So essentially, at some point, we kind of have infinite area that is occurring right over here. So something like this, perhaps. And this is just completely non-integrable. I mean, how do you find the infinite area that goes on over here? So sine x over x is integrable, but cosine x over x is completely non-integrable because of what happens over here. And in the same vein, we also have sine of 1 over x, which goes absolutely crazy when it's near 0. So this is what we call the topologist curve, and essentially it looks like this. So it calms down when it's not near 0, but then it speeds up and speeds up in frequency until eventually the frequency is absolutely huge. And then as you get away from the origin, it slows down again. So this is what sine 1 over x looks like. And as it gets infinitely, as its derivative goes to infinity, right around here, this is pretty much impossible to integrate, as you can see. I mean, how do you even integrate this? Because all of these little infinite humps, they themselves, you have to add them all together, and it's just an absolute mess. So these are two functions that I would say are completely non-integrable. So if anyone knows of anything else, I'd be happy to show that. But yeah, so that's yes, 1 over x is indeed integrable. Of course, not from negative infinity to infinity, but it is integrable on the positive because turns out that this area over here is finite, kind of like the area of a square minus a quarter circle. Turns out that this area is, of course, finite, and the integral of it is ln over x. So, I mean, I don't remember the proof of it off the top of my head. Let me think about if I can derive it quickly. But let me see. Can I derive that? No, I don't think I can. But I think I might be able to actually. Yeah. So we already know ln of. So what we want to prove is that ln of x and the derivative of that is equal to 1 over x. So then d dx ln e to the x, this is obviously going to be equal to 1 because it's ln of e to the x. Wait, no, this is going to be equal to 1 because it's the derivative of just x, right? So then that should give us this, by the chain rule, is just going to be equal to f prime of g of x times d prime of x. So we have whatever ln, the derivative of ln is, times what's inside, multiplied by what's inside. So that means f prime of e to the x has to be equal to 1 over e to the x. So by the same logic, f prime of x has to be equal to 1 over x. So I think it might be a shaky proof, but I think it works. So that's how I would prove that the derivative of ln x is equal to 1 over x. And thus, by the same reasoning, the integral of 1 over x is equal to ln x. So since ln x is not defined on the negatives, though, and not at 0 either, that doesn't mean we can integrate it from minus infinity to infinity. It just means that we can integrate it from 0. It just means we can integrate it from 0 to infinity. So thank you.
Thank you very much for